Today we're here to discuss medical complications of airborne diseases in semi-tropical climates. No, biomass gasification, and toward the end I'd like to give you a special treat and talk about rocket stoves, which do gasification and combustion of the syngas upon creation with self-induced draws. It's kind of really an exciting technology that is being used in third world countries. But before we actually begin, I'd like to tell you a little bit about ourselves. My name is Greg David. This is my colleague Patrick Rowe. We are both members of Sustain Jefferson. Sustain Jefferson is a not-for-profit organization that uses the philosophy and framework of the natural step to help understand what sustainability is and then try to implement it within our culture, society, lives, etc. So it's a fascinating group of people, and the natural step is a fascinating framework for sustainability. We'll be doing a presentation tomorrow at noon about the natural step. It's probably, I think, the world's best scientific and ethical framework for determining what sustainability really is and then implementing it within your lives and your culture. But the reason we're talking today about biomass gasification is when a group of us got together, we do study circles in the natural step. We study a book and you get together with your colleagues and a facilitator guides you through a bunch of Socratic questions so that you can internalize the material. And when we talked about energy, we got all excited about this biomass gasification, and one person in our group said, you know, I have plans for a biomass gasifier. And I said, geez, I have plans for a biomass gasifier too. And then the next week when we met for our weekly discussion, lo, they were the same set of plans, and we said there is something about this, let's build it. And really that was the initiation of our energy project team, and we call ourselves Jefferson County Community Supported Energy. Has anybody ever heard of community supported agriculture? Okay, so we are attempting to do community-supported agriculture is where a farmer will grow vegetables, flowers, and herbs, and then market in a cooperative type method, sell shares of those vegetables to local people, and it's a way to connect with your local farmer. We are attempting to do something very similar with energy, and we're producing syngas with biomass gasifiers, but we're also doing micro-scale ethanol ethanol production and micro-scale methane production. But so we got together and we were so excited. Wow, everybody wants to build one of these things, and a project team developed. People, after they finish these discussion courses, want to take this newfound knowledge and wisdom with these newfound friends and do something with it. And so we offer people, when they finish their course, we offer, become part of our group. We have project teams in ethanol, we have project teams in gasification, we have project teams in raised bed gardens. We call them Earth Victory Gardens. It's a composting, rain barrel, and raised bed garden, helping people understand how to manage the material and energy flows throughout their household. And the reason we wanted to do this was we understood how important biomass gasification can be in solving our local energy needs, because for a number of reasons. One, you can grow your own biomass at your home, you can grow your own biomass at your farm, and the scale that we work at is, we call it appropriate scale. Appropriate scale for individual households and small scale farming or large scale farming, but it's something that a farmer or a homeowner could grow their own biomass, produce their own heat and electricity, you know, use the gasifier to create syngas, which is 20% hydrogen, 20% carbon monoxide, both combustible gases, and 60% nitrogen, the atmospheric background gas. And use that to turn a genset to create electricity, but glean all the heat out of the system that you can, so that you can have your own cogen plant at home, and especially on the farm. And so we'll go through the technicalities of it as we go along. If people have questions, feel free to interrupt me. If I lose my voice, Patrick will take over, but I talk too much on these weekends, I think.
And for those of you that are not from Wisconsin, the white stuff is called snow.
So we got plans for a FEMA downdraft stratified gasifier, and it's one of the more simple gasifier designs, but it's also one of the better gasifier designs, and we built it and it turned out and it surpassed our wildest expectations, and we have some pretty wild expectations. And as you can see, this is the gasifier. These are extraction ports for the char that accumulates in the bottom and for lighting the mechanism from the underside, and a shaker mechanism off on the right side or left side. And the gasification actually occurs in the reactor core in the center, and we'll have diagrams a little bit further down in the presentation so that you can actually see that happen or understand where it is happening. But one of the things we pride ourselves in is we like to use recycled materials, reused materials, salvage materials, scrap materials. And this FEMA downdraft stratified gasifier lent itself perfectly to that. We got to use an old steel drum, a recycled 2-inch pipe. We did have to buy the pipe fittings and nipples. The most expensive thing on here was a $45 4-inch pipe cap. So it was mostly the middle of winter when we put this thing together, and here you see the gasifier linked with a 6-foot piece of pipe, and this is the filter mechanism. It has a baffle in the center, and the gases go down through a stone filter and come back up through a wood chip filter and exit pretty well scrubbed, but not entirely scrubbed. And what we're trying to scrub out of it is tar and a little bit of water. If you burn the thing practically all day, you'll end up with a glob of tar about so big, which is pretty insignificant, but it will foul an engine eventually. And this is the reactor core. This sits down at the top, and the magic occurs in this area here. It has a pan that sits on the bottom, a stainless steel pan that we drilled holes in, kind of like a colander, and it's suspended from a chain. You can see the brazed in bolts so that when we set the thing down on top of the stove it nestles in place, and you use high temperature silicone sealant to seal it in place so that it does not leak. You do not want to have leaks in your gasifier because it's done with a fan. Almost all gasification, most gasification occurs using a fan to create the draft. And most people will have a fan on the far downstream end, so you're sucking air into your gasifier, and you use that air for the combustion process. And you do not want to mix air with your syngas because then it becomes explosive. Syngas is actually quite safe. It's hydrogen and carbon monoxide. You don't want to breathe it for obvious reasons. The hydrogen won't hurt you, the nitrogen won't hurt you, but the carbon monoxide will kill you dead. And when it mixes with oxygen, it becomes potentially explosive, so you want to make sure that all your seals are very well done and airtight. You can hardly see it, but that's one of our colleagues, Patrick Rowe. This was the first time we ran it, and we turned the fan on, and we had this great suction, and you could hear the fan, and he was all excited about that. Patrick is a research scientist in the field of biological systems. What?
You're talking about me, no.
Oh,
that's the other guy.
the other guy, Doug Johnson. Doug Johnson, sorry. Patrick has his own unique specialties and his own brilliance. So here you see us lighting our gasifier. What we do and it took us a while to figure this out. When you have your gasifier all built, you want to fill the bottom part of it full of charcoal. Your reactor core is generally about 20 to 24 inches long. You want to fill the bottom half of it with charcoal and light the charcoal and get it red hot and glowing before you add your fuel to it. And then you have a real quick light, and we can have syngas ready to run an engine in less than a minute under ideal circumstances. The first time we lit it, it took us 45 minutes of the worst smoke and air pollution you can possibly imagine, but magically we can learn from our mistakes. What we like to burn, what burns the best is pelletized wood. Pelletized practically anything works. We have pelletized sewage sludge mixed with city waste leaves and things like that. That burns pretty well. One of the things that does not work very well in our gasifier because of the extraction mechanism for the charcoal is anything with a lot of silica in it, like prairie grass, like corn stover. That tends to form a mass of glass, vitrified solids in the bottom of it, which eventually clogs it. You could design the system around that so that you can extract out, but our system does not handle that. One of the and here you can see we've lit the core and now we're ready to push the stuff in. Typically you would put a hopper on top of this. Once you get it lit, you dump your biomass into the hopper and it could gravity feed as long as you're using pellets. If you're using chipped wood or something of that nature, it tends to bridge more, so you have to design your gasifier with a slightly bigger reactor core so that it flows more evenly. And you may have to have a poker mechanism to break the bridging that occurs with the less processed fuel source.
But it will burn.
Yes, but it will burn them very well. There you see the biomass being combusted. Here you see Doug excited about our first burn, and you can barely see the hydrogen and carbon monoxide burning in the nice flare head there. Another flare head. When another flare. Here we're experimenting with injecting air in via mouth pressure just to cause a blowtorch type effect.
The real topic to that one is, no, you're supposed to blow, not suck.
This was the working diagram for our gasifier. This is actually a thumbnail sketch, or in this case, those are my toenails. I had the sketch down and took a picture like this, but we're sophisticated on some things, but the thumbnail sketch worked fairly well for us here. These are some of the parts, and here you can see 100-pound propane cylinders. This is actually our second design. We recognized some flaws in the FEMA design and we wanted to improve on it, and we went to a different quality, thicker quality propane cylinder. The barrel wore out after about all the joints and stuff where you're wiggling it tended to just fatigue and the metal started to crack. But
barrel wore out?
Not this barrel, in the first one.
The first one we showed?
The FEMA,
Okay, that oil drum. Yeah,
yes, that wore out. Yeah, you know, it's only 18 gauge or something like that. Yeah, please do. Thanks for asking and doing it. So now we're using propane cylinders or tanks, which are usually readily available for free. In fact, the man delivered these to us. He delivered about a dozen of them.
Very happy to get rid of them.
Yeah. This was before. This was when scrap metal didn't have much value to it, but the prices fluctuate. Well casing, 8-inch well casing in the cooling tower, and some salvage pipes here in the reactor core. This is a 6-inch well casing reactor core, and even the plate material, a bulldozer ran over it, so it was a little crimpled, but we could still get a lot of good usable pieces out of it. So the materials are relatively cheap, and if you're scavengers like us, they're quite cheap. This is the cooling tower, this is the top, and this is the bottom, and the gases flow in at the bottom and travel up and travel out the top. We'll have more pictures here in a moment. Inside that cooling tower are a bunch of copper coils. These copper coils, there's 100 feet of copper coil within the cooling tower, and each one is consecutively smaller so that they nestle within one another, as you can see there. And then inside we put a muffler that we cut the top ends off of and weld a plug on so that the gases have to travel between the tight spaces between the coils. We don't allow the gases to travel up the middle, so it's really coming in contact and going through a very convoluted maze of copper coil.
So you put a muffler on?
We took a piece of tailpipe. It happened to be the exact diameter we needed. We just welded a plate on the end and shoved it up the hole.
Just to act as a stopper mechanism.
Yeah, because the gas would tend to come in and go right up to the least path of resistance, which was right up the middle and right out the top, never touching the cooling coils. So by diffusing it, causing it to go to the outside edges, it has to deal with the copper.
And the reason for cooling?
When the gases come out of the gasifier, they're about 450 degrees, and this much syngas at 450 degrees is about this much syngas at 70 degrees. So you have quite a bit of higher BTU content per foot. Plus, your contaminants are vaporized tar at 450 degrees in water, and when you drop the temperatures down to 70 degrees, both those materials will condense into microscopic droplets of tar and water, which are more easily filtered out than in the secondary filtration systems.
You don't need that as long as you use it for heat.
That is correct, yeah. That is correct, yes. This is how we make our copper coils. We built a mandrel, and we use the same gasifier and the cooling or the scrubber as a mandrel shaft. And then what we did was we took 4 different stages of mandrel. This is a 3-inch PVC pipe, a 4-inch PVC pipe, some pieces of wood wrapped around a 4-inch PVC pipe. So this is 3.5 OD, 4.5 OD, 5 5/8 OD, and a piece of well casing that was 6 5/8, 6 3/4 ID. And then when we wrap the pipe around, you get those pipes, those coils that you saw in the previous picture. There we are getting ready to wrap it, and that's what it looks like wrapped. And one guy is just wrenching it. You know, you could buy a big expensive lathe and do this or something, but again, we like things simple. You know, keep it simple, right? And this way you can create the things. The expense of doing this is practically zilch. That's not the right word. There's another one of our project teams, Rob Frost, who's doing a kind of a permaculture class here. There you see the manifold soldered in place of the 4 copper coils. There you see the parts of the manifold, all readily available parts at the hardware store. This is our standard poodle burdock standing next to the reactor core.
It's not nuclear either, is it?
No, it isn't. And that's the our 2nd generation gasifier. We're on to our 4th generation now. This is the 2nd generation. This is the whisker plate. The reactor core rests not quite on this. There's about 1.5 inch space between the bottom of the reactor core and this whisker plate, and then this whisker is activated by a little mechanism that you just spin with your hand, or we can mechanize it too if we want to mechanize the thing, but it gets requires a bit more work and process. But it spins around and it knocks the charcoal out of the bottom of the reactor core, so that you can keep the reduction zone within the reactor core at the right distance and toward the middle of the reactor core. And interestingly, biomass gasification, depending upon how you do it, can be a carbon negative process. It is carbon negative when you think of it in the term of a system, because the woody plants or the woody plants have captured carbon dioxide from the atmosphere and stored it in the form of sugars and starches and cellulose and lignins and things of that nature. And then when you put the woody biomass into the gasifier, over 50% of the carbon remains sequestered in the bottom of the stove. So it's one of the very few carbon negative processes. And anybody go see Bill McKibben today? You may recognize how important that really is. And very few energy systems are carbon negative. You look at something like windmills or solar panels, and people say that those are carbon neutral. They neither put carbon into the atmosphere or take it out. I would argue that they are slightly carbon positive, because there is embedded energy and ecological footprint, if you will, contained within the windmill blades, the silicon, the towers, all the grid and stuff necessary to make to transmit the power that you are creating. So it's slightly carbon positive. When you think in terms of fossil fuel, hugely carbon positive. All that fossilized carbon being extracted from the Earth's crust, burnt, and put up into our atmosphere. This is one of the few systems that is carbon negative. And you can do really, really good things with that carbon that comes out of it. It's essentially pure 100% activated charcoal, and you can use that for filtration of water, of air, all sorts of different things. Yes?
Do you make brushes out of it, like electric motor brushes?
Yeah, I don't know. Maybe you'd have to reformulate it. You know, it's just charcoal in nice usable forms. You could burn it, then you're more carbon neutral. But what we do with it is we spread it on soil. We use it as a soil amendment. And has anybody ever heard of terra preta? Terra preta is supposed to be like one of the most fertile types of soil on Earth, and it's based on carbon. And the reason it's based on carbon is we are all carbon-based creatures, you and I. And I know this is true because I learned about it on Star Trek. The reason we're carbon-based creatures is because carbon has an infinity for combining with all sorts of different molecules. And when you put this pure activated carbon onto your soil, nutrients that were not available suddenly become available to plants. And little microcosms of life begin to occur around these little chunks of charcoal. And when you have, you know, it starts the basis of the food chain, if you will, and all sorts of things start to grow around there. So you have these microcosms of life, and each step of the food chain provides fertilizer and nutrients for the next stage, and it really creates very, very healthy, dynamic, very actively alive soils.
It seems a little off topic, but I just wanted to define sequestered means that carbon, once you put it in the ground, stays there, doesn't get into the atmosphere.
Right. Sequestration means locking it away. Where the trees and the plants remove it from the atmosphere, we utilize part of it, and then it is locked away in the form of charcoal. And that charcoal is very, very stable. Thank you. It's very stable. It's not going to, you know, it's going to last thousands of years in the soil. And it also creates all these biological life systems to start to form around it, and I understand that it also will attract carbon out of the atmosphere into those types of chains, so really a good thing. This is the whisker and the auger activation method. You screwed a little crank here, it turns the mechanism in the wheel on the bottom, and that turns the auger that removes the core from the upper part of the gasifier, and also it spins the whisker to remove the whisker from the reactor core. And then we seam the two pieces together. We just weld on little steel tabs and put a bed of high temperature silicon here and bolt them together. This is a side view of the mechanism, the activator and the belting system. This is the fan that makes the thing go. It's an automotive heater fan, a 12-volt automotive heater fan, and that draws the air and the gases through the entire system. And then it goes through a valve and into a manifold so that we can send it to engines or whatever we want to send it to. The automotive heater fan isn't really very good for run on 12 volts to draw enough air through the gasifier to create high quality syngas. We have a variac, a variable speed a variac is a gizmo. What's
motor speed control.
It's a motor speed control, yes. And
we run an AC motor now.
Yeah, but we discovered there's something called superficial velocity. Remember that term? I'll come back to it in a moment here. So there's our fan again. And then we use a barometric trap, a bucket of water that we slide up onto the bottom of the cooling tower so that any water or tar that is collecting in the system kind of drips down and is collected into the bucket. And that barometric trap does two things. It seals the bottom of the cooling tower, but it also acts as a very good collector for the tars. The tars are very similar to creosote. You could probably use them for fence posting material or wood preservative. It's called Stockholm tar back in the 40s and 50s when gasification was incredibly popular. In fact, maybe I should go on a slight tangent here. Back in World War II, There were millions of these types of gasifiers, maybe not quite as sophisticated, although they really worked the system out well during World War II, because there would have been a famine in Europe because all the oil and gas was going into the war effort. And on the fronts of tractors and the back of pickup trucks, city fleet, bus fleets had gasifiers, and they would pump up big balloons on the top of their buses, and each time the bus made a circuit, they would fill up the balloon on the top of the bus because that was the only fuel source that they had to run their internal combustion engines. This is the whisker plate with, you can see the whisker there. There's Patrick sealing in the top of the reactor core into the gasifier. There's Patrick proudly displaying the gasifier. I'm not in any of the pictures because I'm the photographer. And here you see some of our high-class quality materials that we use.
It's actually pretty good steel.
Yeah. And this is after a salvage trip to the junkyard. You know, pennies on a dollar. All different sizes so we can make different reactor cores and different heat exchanger mechanisms. And we're using the same materials on our rocket stoves now.
That's just a bedliner from a Toyota though, right?
Right.
You could probably get a gas bottle that was large enough you wouldn't even have to connect two together.
That's probably true, but connecting the two gives you something. Where they come together and where the auger is acts as an airlock, sort of, so that you can unscrew the bottom and extract charcoal out. And if you have an automated system, which is where we were going with that, you do not want to introduce like large quantities of oxygen into the thing while it's burning, because you'll have a minor, very minor explosion, which is actually very exciting. We've done this a few times. But it causes a burp to occur in the thing, which will blow all your glowing charcoal and fuel out, and also empty your water bucket on the barometric trap. So it's recommended you don't do that.
That's another reason we used a bucket of water at the bottom, because the amount of hydrogen in that, contained in that column, if it does flash and you had it solidly sealed, the only two places it has to go out is the intake and the outlet. By using the water, it has mass, it can move it, and it moves it very slowly. It just kind of overflows the bucket. So it's a safety valve as well. Yes, that is very true. Good point, Patrick. We'll come to that in just a few pictures, okay? It's down here. It's between the top and the bottom half. This is what happens in a gasifier. In fact, this is our third generation design where air comes in and is actually preheated in the plenum area and then goes up against the gasification and pyrolysis and combustion zone where it is further heated. So you're putting preheated air into your gasifier, which raises the temperature and creates a better syngas quality. Now, a couple things happen within this reactor core. You have the air flowing in, and as it gets close to the combustion zone, pyrolysis occurs. Pyrolysis is the vaporization of the volatile organic compounds contained within the fuel. They instantaneously mix with the oxygen that's flowing through it, flow right into the combustion zone where they burn. Because it is such a tightly controlled and focused burn, it gets up to over 2,000 degrees. And this is where the magic starts to occur. You have your speed, your superficial velocity. That's the speed of the air traveling through the reactor core. That needs to be adjusted to a nicety. And you want to limit the amount of oxygen flowing into it, and that is done with that superficial velocity. And if this is the range of superficial velocity, over here you have really dirty combustion like those outdoor wood burning furnaces that smoke and pollute the valleys all over the place. And then as you get up and push more oxygen through, you get cleaner combustion, and then up in here you get very clean, thorough combustion, and gasification starts to occur. But you have kind of dirty gasification because it's not as hot as it could be. You get up into this zone of superficial velocity and you have nice clean syngas. You get up over here and you're pushing so much oxygen through the reactor core that you actually have surplus oxygen, and it begins to consume the syngas right where it is created. And you get over here and you have blast furnace conditions and the whole thing melts down. You probably want to avoid that. So you need to we sort of monitor that through indirect observation. The quality of the syngas coming out, how much tar is in it, how much BTU content is still left within it, and things of that nature. And you can, after a little bit of experience, you'll be able to figure that out. So now we come to the really fun part. You push enough oxygen through so that all the oxygen gets combusted right after you've combusted all the volatile organic compounds within the wood. Then you have like 2,000 degree temperatures in an oxygen-free environment. And the products of complete combustion are carbon dioxide, water vapor, in this case charcoal and heat. Now those two products, carbon dioxide and water vapor, cannot exist in that environment. It is physically impossible for it to exist in there, and it goes through a process known as thermal destruction, and they are thermally destroyed, and they're forced to recombine and form hydrogen and carbon monoxide, syngas, producer gas, wood gas or manufactured gas. And it's 20% hydrogen, 20% carbon monoxide, and 60% nitrogen, more or less, that comes out of the outgas port.
Could you repeat that last bit, the percentages?
20% hydrogen, 20% carbon monoxide, and 60% nitrogen. That's the atmospheric background gas. And this is a top view. You probably can't understand it because I can't either, so we'll move on. This is the parts list for the thing. Okay, now let's see. Oh, we don't want this to happen. Let me do an escape here. So this is the diagram of the top half. You can see the whisker plate is suspended off these steel bars. In our third generation, we ran these threaded steel rods all the way up through the top plate so that you can adjust the height of the whisker plate from the top without having to disassemble it and make your adjustments. The whisker knocks the charcoal off the bottom of the whisker plate. It collects in this zone and forms that air trap or air blockage, and then when the auger spins, it extracts the charcoal from the upper half and drops it into the bottom half where we can remove it. These diagrams are all available online. If you go to our website, sustainjefferson.org, there's links to the 7 movies that are up on YouTube, or you can go by the DVD at our booth. It's a much higher quality so that you don't have to watch the rinky-dink little picture on YouTube. But then this is the bottom half of the gasifier. The charcoal collects down in the bottom, and this has enough capacity to probably store, depending upon how much you're going to burn your gasifier, a couple days worth of charcoal. Typically, what we are thinking is if you're trying to electrify and heat your house, you probably have to run the thing 2 to 6 hours per day. And you want to run the gasifier, as we talked about earlier, with superficial velocity, like at 80% capacity. If you run it at low capacity, you have really poor quality syngas. And if you want that high quality syngas, then you want to run it at a higher temperature. And where was I going with that?
Do that as airflow.
What's that?
To do that as airflow.
Oh, yeah. So the airflow controls that, but you're much better off burning the thing at a high capacity and then having a thermal storage tank with the system. So if you're going after thermal heating, rather than burn your gasifier at a trickle charge all day long, burn it nice and hot and fast, use heat exchangers, extract the heat out of the gasifier and the syngas, and then store it in a thermal storage tank of hot water and use that to heat your house. And then tensioning mechanism for the belt, you know, it's just really simple, a pipe within pipe so that you can put an adjuster mechanism on and make your belt tight. Another one of those confusing top draws, top views. This is one of the other designs, the newer designs, where you can have the preheated air going into it. There's another design of gasifier called an invert gasifier that has tubes running down that preheat the air and inject it in at the reduction zone. This essentially does the same thing. The air goes in and then gets introduced right in here, kind of at the funnel where it's that's where the reduction zone would happen. Yes.
What are you doing to measure or determine the quality of the syngas? How are you saying that? How are you?
Mostly through the direct observation. You can put in line a cylinder that you pack full of like pillow fluff or something like that, polyester pillow fluff. Like our 2-inch pipe would go into a 4-inch pipe. You'd pack it real loosely with pillow fluff. It would actually be a filter, and then the pillow fluff would fill up with tars if you have dirty syngas. And you can time this. So you stick it in there, you run it for a minute, 5 minutes, and then you visually inspect it, or you could do a weight analysis where you weigh it before and after, and then keep track and you understand how much tar is in it. As far as the fuel content, you'd have to have a capacity and do a test to see how many BTUs you can extract out of the syngas.
But if you just measured one of those components, whether it was hydrogen or carbon monoxide at 20%, would you be pretty confident that you were in that band or not?
Probably so. I think you get you're going to get about 20% hydrogen and carbon monoxide coming out anywhere within this range. It's just that over here you have real dirty syngas, and over here the line between blast furnace and high quality syngas is not like a fine line, it's like a broad area. You're beginning to consume the syngas, you're consuming a lot of it, you're consuming most of it, blast furnace conditions. It's a broad area, so you need to kind of do some experimentation, and you know, you get a feel for it after a while. We have a project team that meets most Monday afternoons at what we call Gasifier therapy session. It's a, what's that? And we get together and we breathe that high quality syngas to enhance our, no, we really don't, but we do get together and we do call it gasifier therapy, but a group of folks, and it's not, you oftentimes say a bunch of guys get together, but there's some gals that are involved in this too. And we talk thermodynamics, and we talk design, and we cut, and we weld, and we grind, and it's also part of a reskilling process. And one of the gals had never run a grinder before. She was thrilled to be taught to use a grinder. She does all of our grinding now. We have another guy, what's that?
Your grinder gal? Oh,
yeah. Yeah. And then we have another guy that was did a little bit of welding, but he learned to weld. Now he's an excellent welder. So we teach these skills to people that come reading diagrams, except for those confusing top diagrams. But people come and it's part of a reskilling process. And anybody ever heard of transition towns? The transition town, like step 9 of the 14-step process, is the reskilling, the great reskilling. And this is part of our effort. We're working on transition town movements with Sustained Jefferson also, but that's part of our reskilling, is to have people come, and you're all welcome to come Monday afternoons at our farm. Everybody should sign up to our listservs. We have 2 of them. If you go to sustainedjefferson.org, somewhere on that website, there's a place where you can sign up to Jefferson County Community Supported Energy at googlegroups.com. And then our other one is Sustained Jefferson at googlegroups.com. But it's how we communicate with one another mostly, and you can expect, like Sunday night, or maybe if we get online and we're planning well enough, announcements, you know, gasifier therapy from 1 to 6 Monday afternoon, things of that nature. Rocket stoves. You know, our group, Sustained Jefferson, we have a project team of about practically 30 people, and at any gasifier therapy about 10 to 15 of them will show up. And we didn't meet much over winter, but when we met in spring, one of our members brought a rocket stove that he built, and it was the coolest thing, and we fired it up. It was the lightweight concrete one that you may have seen in our booth, and we were so impressed with it that the next week we built this rocket stove. And you can see there's diagrams. We're feeding it sticks, and you can see the parts that we use. And when we build these rocket stoves, we use only the highest quality rust finish on these things. And this is genuine rust. This is not the cheap imitation. This is authentic. So Only the highest quality materials. But you know, that is a self-induced convective airflow that occurs just from the combustion, and I'll explain that. You can see the fire burning underneath there. This was all filmed, all the pictures and the films were taken with my iPhone, which, you know, is just amazing, isn't it, what these little devices can do. So now we're burning chipped wood, and you can see us poking it in. You do have to tend this thing, you know, if you're using sticks. Yes? Yes, that's exactly right. The air is going in on the underside and the fuel is going in on the top side. The grill, you'll see, is fluted so that you have good air passage. This is the basic design. This is the barbecue design. This is the wok top design. And you know, this is a disc from Farm and Fleet, so again, only the highest quality materials.
See, I go away on work for 2 weeks and I come back and all we're building is rocket stoves now.
Not yet, pretty soon, pretty soon. Yeah. These are so simple, you can remember all this stuff. This is an interesting thing. Flask, you'd use one of these propane tanks and you weld a steel rim on it. You cut it out to about 11 1/4 or 11 1/2 inches, and then a 12-quart stainless steel cook pot will fit right down inside it so that the flame goes and hits the bottom and goes up the sidewalls. And truly, this is incredibly efficient use of sticks around your yard. And rocket stoves are being used in third world countries and encouraged because typical folks in third world countries will use a 3-rock stove with a grill on top, and they're really not very clean, and people have all sorts of pulmonary diseases and eye diseases from the rather poor quality burns. These rocket stoves burn so cleanly that they're being used in third world countries oftentimes.
Note to most, do not use aluminum utensils because it will tend to melt them.
Yeah. Here you can see the flutes cut into, you know, a kind of a fork thing so that the air can pass through. And yeah, you know, again, this just amazed us, the draw of this thing, and we're now beginning to think, now how can we make this gasify? It probably is gasifying. Anytime you have high temperature fire happening, pyrolysis is probably happening, but the syngas is consumed as soon as it's produced, you know, in the flame head. Yeah.
Yes.
So let's see, there we're taking off the grill top, and there you see all of our design engineers oogling and ogling over it. We're very easily entertained. Here is a diagram. I mean, you can remember this now, right? Yeah, the air travels in the bottom, the fuel is pushed in the top. I did end up cutting off the end of it because when we burnt it hard and fast, charcoal built up and filled up the grate, and it kind of choked off the air supply. So when we start this thing now, we throw a little bit of old charcoal down in the bottom to plug that hole, and then as it begins to build up, you just take a steel rod and plunge it out a couple times and drop the charcoal to a nice level. So you want to try to keep a bed of charcoal in there to add your latent heat source, and then you know, it just vaporizes, pyrolyzes the fuel source and combusts it really, really well.
What's that collar have up there showing?
What, this?
On down. Yeah.
Ah, this.
Somebody noticed.
Somebody noticed. Darn, that's our secret. Okay, now I got to swear you all to secrecy here. This is where a stainless steel grate will go. And let me just jump ahead a slide. This is the wok top design. You know, actually we welded on little tabs here rather than on the wok top, and then it rests. And you want the space to be approximately equal, the whole volumetric gap to be about the same size as your chimney. This is how the stew pot would work. The hot flames, you know, really hit all sides. You got to leave a space here. The handles hold the pot from dropping down inside. Incredibly efficient. You know, you can boil water, and you'll just be amazed. at how short a time. This is our next design, where instead of just cutting an end off with a torch, we cut a hole in, welded a 2-inch pipe nipple, and then you can screw a cap on, And then the steel ring gets short. You cut off a piece of your well casing, cut out about 1 inch length of it, kind of make it a slightly smaller diameter, weld it in at that point before you weld this on. And then you cut a stainless steel grill grate, just the right size so it drops inside. Then you can fill this whole thing up full of pelletized wood or chipped wood and put a fan on this end. We typically use fans that like computer fans, salvage computer fans, and you light the thing on top and you blow your air through here, and now you have a inverted downdraft stratified gasifier, and we have one over at our stand where again the fire is burning in this direction and the air is going that direction, and that's what gives you the gasification. So these can be used for biomass gasification also.